All right, welcome to the first lecture in Physics 120, Introduction to Physics. And this one is about what is science. Physics is one of the sciences. Science is both a method and a body of knowledge. The method's often called the scientific method, and it's a way that we have of adding to the body of knowledge, which is basically, sometimes people call it common sense on steroids. It involves making some type of hypothesis that has to make a prediction, and then coming up with ways to verify that prediction. And then based on the results of your test, your hypothesis is either verified, disproved, or more often than not, it gets revised, and you go through the process again. It's a circular process like this thing up here indicates. In a course like this, in an undergraduate physics or chemistry or biology course, then really what we're studying is the body of knowledge that's already there, the basis of which you'll use for more advanced classes. And so we're not so much using the scientific method, but we're studying what's already been verified by the scientific method. We're looking at the facts, the laws, and the theories. It's important to understand what makes a set of ideas part of science. And if there's a single phrase, it's predictability. In other words, if I've got a hypothesis, then for it to be scientific, it has to make some type of prediction that I can then verify by measurement. Measurement and science are intimately tied together. Science advances not often by proving things true, but by proving all other explanations are false. In other words, we usually disprove a statement. Because if I make a prediction and it turns out to be true, then I can use those same ideas to make other predictions. As long as those predictions keep turning out to be true, then we'll add that to our knowledge. But it could always turn out that under certain circumstances, it predicts something wrong. So it's ever-changing, never has a final result. But it's not the only way people have of thinking about the world by any means. There's literature. Literature is not a science. It doesn't mean it's not valuable. It doesn't mean it's not important. History. People study history for good reason. Art, music, religion, all of those are different ways of looking at our experience, but they're not science. They don't have to make predictable projections like science does. Measurements are a hallmark of good science, scientific measurement, and that's one of the things that we'll try to do, and it's one of the things that many of you will be training for some technological field in which you make measurements, and measurements are fundamental to what science is about, and we will make some measurements or give you measurements at times and let you manipulate them. Now, let's get some of the terminology. One of the things we have to deal with in the sciences is the words that we use have often been used in everyday conversation, but they mean something different. Usually it's because in a scientific context they mean something very specific. And here's an example: fact, law, theory, and hypothesis. Fact is something that's highly certain and very, very specific that can be verified over and over again. It has been verified over and over again. A law, it usually is something that explains several facts, but it's very limited in its application. A theory is much broader. It has been tested and verified. It's a way of thinking about. It may not be all-inclusive. We'll talk about some theories that we know to be true in limited circumstances, but it doesn't contain the uncertainty. I mean, in everyday conversation, I might say, well, that's just a theory, but that's not the way we're using it. That the phrase we should say there is it's just an hypothesis. Hypothesis is uncertain and to be tested. Theories have been verified. The theory of gravity, theory of relativity, the theory of germs, all of these things are broad. So it's a matter of scope and not how uncertain we are. If we're not certain about it, it's an hypothesis. Theory explains laws and facts. Law will explain one or more facts, and then facts are the most fundamental. For example, we're going to talk about Newton's theory of motion, which includes his 3 laws of motion, the law of gravity, and concepts of energy and momentum and friction. That's very broad. It's about how things move. Turns out, though, that we know it doesn't always work. So there are some things about it that don't quite match the real world, and we'll talk a little bit about their applicability. If things move very, very fast, near the speed of light, then it'll give the wrong answers. If things are very tiny, like the size of an atom, it'll give the wrong answer. So it is a valid theory if you use it in the context. I mean, that's 90% of engineering is done with Newton's laws. And they work very well. Your cars run, the bridges stay up, your houses stay up. So it's an all-encompassing theory, but we also know when it doesn't work. Another question that often comes up is math one of the sciences? It's the language of science, and we'll do some math. Now, there's a very minimal math requirement for this course, so I'm not going to have you do any complicated algebra. We'll mostly plug numbers into equations that you're given. I won't have you manipulate those equations, other than maybe very simply. We'll show you how to do that if we want you to do it. But there's a fundamental difference between math and science. Math is axiomatic. Science is not. Axiomatic means that math start with in a field of math, you start with a set of assumptions and you draw the logical conclusions from those assumptions. And you don't have to compare it to the real world. There are lots of mathematical things that don't apply to the real world. In fact, there's a famous mathematician from around the World War I era who famously did math that he hoped would not be able to be applied to the real world because he was unhappy that they used his earlier work in World War I to kill people with. So, but math is not science. It's its own beast, if you will. But it is the best language that people have found to express most of the sciences in. Now, not everything in the science is amenable to mathematics, particularly in things like geology, medicine. There's lots of things there that aren't necessarily mathematically oriented. But nonetheless, it's the language of most science, and particularly it's the language of physics. It lets us say things unambiguously, and that's the bane of science, is trying to find out something about the natural world and describe it in ways that are always true, and regular language doesn't do that very well. Regular language is unambiguous. So even in math, sometimes you have these big long explanations of what a very simple thing means because regular language is not very unambiguous. It's ambiguous with its words, and so it can be difficult to express something unambiguously. Equations, though, are totally unambiguous, and that's one of the big differences. Something that lay people don't understand, and really, unless you've done some graduate level research, that's the nature of proof. Mathematicians prove things true. Scientists prove things false. We can't prove something absolutely true in science because the next experiment may come along and show that the prediction's not correct. Science refers to levels of certainty, and we often make a prediction and try to prove that and see if that prediction is true or not, but it's not the final word. Even scientific laws are relative to the situation. So, scientific attitude is one of inquiry and experimentation and willingness to admit error and willingness to say that when the data or the evidence shows that what you've been thinking is not correct and needs modifying, that's the scientific attitude, that when you're willing to modify. What is physics? We're going to be studying one of the sciences. Basically, it's the scientific study of matter and energy, which includes almost everything. It's often called the fundamental science because in many ways much of biology and chemistry and geology and medicine is applying fundamental principles from physics. It's the most fundamental of the physical sciences. It's the foundation for, like we said, chemistry, biology, geology, astronomy, pretty much all of them. Meaning that the ideas that are used there are more simply expressed in physics very often, like energy is a good example. Now would be a good time to see the range of sizes that we're going to deal with. There's a video out there that I've put in Canvas that you'll want to watch called The Powers of 10. So now would be a good time to go watch that. The classical branches of physics are mechanics, thermal physics, E&M, waves, and optics, and we'll touch on all of those in this class. And then modern physics includes special relativity, quantum, nuclear. We won't really deal much with that because our focus is going to be mostly classical physics, though there will be some references to these things as we go through. Physics is about measurement. Measurements are done with numbers. Numbers represent physical measurements and must have units. And the next part of this module, we're going to talk very specifically, hopefully most of it will be a review about numbers and how we want to express our measurement using numbers and some basic rules that we want to use. For the next class, you need to try to make sure and get your textbook, and you can do that either by ordering a printed one or you can just get the access code to Mastering Physics, because there's an online version of the textbook inside Mastering Physics. And read Chapter 1 and make sure you can log into Canvas and look at the syllabus. If you have any questions, shoot me an email.